Happy Thursday, everyone. Does anybody have any exciting questions about assignment 1? Usually people say, "Oh, Bob, I don't have a question today, but I just wanted to thank you for giving us this assignment. Like, I've learned so much. Thank you so much."
Thank you so much for feel under pressure.
That's usually what happens.
I will dream about it. Like
You'll have dreams about this assignment if you do the assignment, in those hours, those last hours before you go to bed, right? I've definitely had that experience. When I was a student, I used to do my programming sometimes before I would go to bed. That's a mistake, right? Because you stop and you go to bed and your mind is still programming. That's not a good idea. So if there are no questions, that means everybody's happy. Casey.
Yeah. You say you're supposed to use 5 different tools.
3 tools.
3 tools.
Yeah, doesn't it say 3 tools?
Yeah,
3 tools, 5 different visualizations.
Can we use more than 3? Can we use more than 3?
We can use more than 3, yeah.
Or less than?
What was your question gonna be?
I was going to say, if you used 5 different tools, could you use the same tools?
Yes, you can use the same tools for the 3D. The 3D part doesn't require any new tools, so to speak. Yeah, you can use the same tools. Any other questions?
Or less than? Less than 3?
You can use less than 3, but you won't get all the points if you use less than 3. Yep. Sound good? Come on, the assignment's kind of easy.
Easy?
It's kind of easy. It's just time consuming, but it's kind of easy. Yeah, it's kind of easy. I think this module sometimes is too easy. Before I forget, so I'm going to be away next week in the amazing city of Baltimore at a conference called IEEE Visualization, which is the global conference on this topic. So we're going to have 2 very special guest lecturers. On Monday we're going to have Chow Tong. Has anybody met Chow Tong? He's going to be talking about visualization of this data for assignment 1. That's what his talk is on. But he's building his own customized tool to get the job done rather than off the shelf.
wow.
Yep, exactly. Wow, that's the appropriate reaction. He's also going to be covering the lab on Tuesday because Rich is away on Monday and Tuesday. And then on Thursday, we're going to have Richard Roberts come and give a talk that presents his visualization work. So both Richard and Chow are PhD candidates in data visualization, and they're developing some very cool visualizations to shock the world, to advance the field. So before I thought I would start today with a video. Does anybody know what that is already? What's your name? Andy. I remember you, Andy, from a software engineering alumni. What is this, Andy? A chord diagram. Have you tried it out for assignment 1? Thank you for that. It is a chord diagram. So it's another high-dimensional data visualization. It is similar to parallel coordinates. It's not exactly the same, but it's similar. So every attribute is given a curved segment. So there's 360 degrees. That's one attribute. That could be a healthcare attribute like cardiovascular disease, for example. That's another data attribute or data dimension. And so there's one curved segment for each data dimension. And then if the two dimensions are related, there's a curve, another curve on the interior that connects one to the other. So you can imagine the parallel axes in the parallel coordinates visualization just being reformulated or repositioned in a circle. Now, a polyline and parallel coordinates would show up as multiple curves in the chord diagram, right? So that's how that would. But in the chord diagram, you have the option of showing only one relationship between two variables, as opposed to a whole polyline. In parallel coordinates, usually you have a polyline that spans all the axes. It's very unusual that the polyline doesn't cross all the axes. But here you don't have to connect all the lines, like all the segments on the edges together. In fact, it's kind of unusual to find a curve that's connecting all the segments. And this is a video showing, so that's a lot of curves, right? That's a lot of information. And they're overlapping. It's hard to follow the edges, right? Because the information is too dense for the visualization. So this is just a visualization that's trying to explore ways to reduce the visual complexity and the edge crossings, right, from our graph, our knowledge of graphs, and so on. So edges get clumped together, similar edges get clumped together into bands, right? So that's a number of edges. And instead of, this was done by a Swansea University student, by the way. So there he's interacting with the edges. So this is a focus and context visualization. So he's using his mouse pointer to point at some of the interior edges, and then they come into focus, and the rest go into context, so to speak. Right? And you can click on one of the curves and get only the edges in that category or that data dimension, right? And he's done a few other very, very nice user options. He's also added this option of glyphs. So he's integrated glyphs into the visualization. Wherever, in this particular version of the chord diagram, Mike has extended it so that it shows three-way relationships. So an edge can go from here and then split and join two other data attributes. It shows three-way relationships, which is not typical of chord diagrams. Chord diagrams usually only show two-way relationships. So Mike added the third, and then you can see using glyphs, the edge intersections. You can focus on just the edge intersections in the middle to reduce the visual clutter. That's a different data set though. That's not the healthcare data. That's automotive warranty data. And that video is available on the InfoVis YouTube channel for anybody that likes to see it and get more information. But it's another option in assignment 1. It's a beautiful option. You have to admit it's kind of beautiful, isn't it? And I didn't have any slides. There are no slides on this because I forgot to put in a slide for this, basically. Any questions about the chord diagrams? Good. Okay, so let's finish up this bad boy. This is kind of a dense lecture, actually. It's quite a dense one. Right, we talked about the graphs and their optimizations 2 lectures ago. We looked at a case study. Then we talked about n-dimensional data visualization techniques last time, including glyphs. And we looked at the rugby case study. And then we started parallel coordinates. We showed how to construct parallel coordinates. We showed adding color to parallel coordinates. And now we show a limitation of parallel coordinates, right? This is what happens when you have lots of lines, polylines, right? Parallel coordinates have their limits. So this is part of the inspiration behind assignment 1, right? If you try to just use a bar chart on assignment 1, right, to visualize, I don't know, the 7,000 practices. Imagine a bar chart that had 7,000 bars. It would be hard to see. So the question is, how can we address the overplotting polylines in parallel coordinates? There are a few ways to do that, right? We're just going to mention a few of the ways. One is called brushing, and that means you can select a range of values along any axis. Right here, the user is selecting this range of values, and then all the polylines passing through that range are highlighted, are rendered in focus, where the other ones are rendered in context, right? So here, all the polylines are rendered in this funky kind of magenta color, where the rest of the polylines are rendered in this RGB color map. So now we can see what happens to these and where they go, and reduce some of that visual occlusion. We can also try to make hierarchies out of the parallel coordinates, so grouping lots of polylines together into clusters, and then rendering the center of the clusters with higher opacity, and the edges of the clusters with lower opacity or more transparency. So that's the original, and that's the hierarchical version, right? And you can see things in the hierarchical version that you can't see in the original, right? You can see clusters here inside. Still not trivial. It's still not that easy to see everything. And here's a feature where we can add histograms on top of the parallel coordinates. So this bar sticking out means that a lot of polylines pass through the axis in this range. And no bar means there are maybe no polylines passing through the axis along here, right? Those are standard sort of histograms. That's what a standard histogram looks like, plotted on each axis. And here, they've been given an angle. So the average angle of the polylines passing through this range is sloping down. It's an average angle. And the average angle of these polylines is pointing in this direction. So now you can start to imagine, oh, there's a clump of, probably there's a clump of polylines pointing in that direction, right? And it sort of joins up here too. So that's another way to address the overplotting of parallel coordinates, because this approach can handle any number of polylines, right? Any number, it doesn't matter how many. And that's what happens when you color map. You can color map the angular histograms, they're called. You can join them together to form smooth curves, also called attribute curves. And we can watch a demo video of that, also done by a legendary Swansea University student, Zhao Gao, who's now graduated. Okay. So this is what the angular histograms look like when the user is actually interacting with the software and playing with exploring the data set and using the different user options or selecting the different user options. So the user can choose bars, click on bars, and then they'll subdivide if they want to. And that gives you a higher resolution of the bars, so to speak. It gives you more information. If there are polylines that are splitting apart at multiple angles, that'll show up if you split the bars apart, or it might show up. It might show up. So this is adding the polylines that pass through some of the bins. So the user can select some of the histogram bars, and then the original polylines will be rendered in the background. So you can see what the original data looks like underneath. Not all of the original data, because all of the original data would just turn the whole screen white, or the whole background. And this is the user brushing an axis, so selecting a range, and then showing the polylines that pass through that range on this axis, right? So they're brushing another region, right? The polylines are rendered, all the polylines that are passed through that range, right? And that shows the original lines that are passing through that range, the original polylines. So he can adjust the transparency of the bars and the polylines, right, to get exactly what he wants. And there are sliders for adjusting the transparency of each at the top. Or brush means combining two brushes together. So brushes can be combined using logical operators like and or. Like, show me all the polylines that pass through here or here, right? He could have chosen an and brush that says, show me only the polylines that pass through here, here, and here, which wouldn't be very many probably. But that's just showing how you can combine brushes together into multiple combinations. So that's the logical and operator that we're all familiar with. Everybody's familiar with logical and logical or. Has anybody ever seen this before, by the way? You can find images of this around the university. They're on some of the posters that the university has for College of Science. You can also find this in Swansea City Centre, pictures of this. It's on Princess Way. There's a place, I think it's called the Oriel Science or something like that. It's along Princess Way. It's right next to a cafe. And there are two big College of Science posters where you can find this visualization. I took some photos. So this is also available on the DataVis YouTube channel if you want to look at it in more detail and look at it again. Any questions about this? Looks interesting, doesn't it? Okay, and then, so we saw, by the way, we saw some interaction techniques in the chord diagrams video and in the angular histograms video, right? So we saw the user clicking on different parts of the diagrams, bringing them into focus, and using focus and context techniques and brushing techniques with the visualizations. This is another style of visualization, coordinated multiple views, or sometimes called CMV. So this is combining multiple views of the same data in one visualization system. In this case, it's flow visualization. So that's a cylinder, and that's fluid flow. And somebody is trying to understand the fluid flow, how the fluid flow behaves when it passes that cylinder. That's a very special cylinder, though. That's the cylinder that holds a marine turbine in place. Has anybody here ever heard of a marine turbine before? Or a water turbine?
Yeah, water turbine.
Say it again?
I've
Yeah,
heard
you.
of it.
So the UK and Swansea University are very active in trying to develop these marine turbines. So we all know about wind turbines above ground. These go underwater. And they're propelled, in this case, by the current. Anybody here from Bristol? Like around that? Okay. Is there anything special we should know about Bristol related to this?
I'm not, I don't know. I just went there for one day.
Oh, okay. You're not from Bristol.
No.
Nobody here is from Bristol, right? Any authoritative people on Bristol? So there is something special about the Bristol Channel. Nobody, I don't know, any, Reese?
Would it be that it's one of the most tidally active places on the planet?
Correct. How did you know that?
I did, going back about a decade, I did a lot of geography.
Well done, well done. So the Bristol Channel has the biggest tide gradient, maybe in the world. It's one of the biggest tide gradients in the world. So the difference between the water level at low tide and high tide is huge. I think it's something like 13 meters or something, really crazy. I haven't seen it personally. But anyway, a lot of people are trying to use the Bristol Channel to test out marine turbines, including a lot of people at Swansea University. They want to understand how the flow behaves past the marine turbine. So that's the standard scientific visualization view, and those are streamlines, which we're going to talk about. Now you know about parallel coordinates. So that's a parallel coordinates view of some of the data. And it has different attributes about the flow, like the velocity, temperature, pressure, and the location. This is a histogram of the flow. And those are all the different attributes, again, like velocity, pressure, temperature, energy. There are energy units. These are traditional histograms, right? This is a histogram, a spherical histogram that actually shows the direction of the velocity in 3D space. And this is a so-called streamline graph, which it's just a scatter plot that plots the Z value versus the amount of curvature in space. So we're looking in this case for highly curved streamlines. Now what's special about this is all the visualizations are connected and coordinated to each other. So if I do some brushing here, on this axis, streamlines will be rendered in that it will be seated and rendered in the corresponding positions. The corresponding data will be rendered and updated in all the views. And same with all the views, right? The user can select some bars in this histogram table, and then that corresponding data will be rendered in all the other views. And that's called coordinated multiple views. So we can watch that too, instead of looking at boring slides. I like videos a lot better than slides. Does anybody else like videos better than slides? Extra points if you like videos better. So this is somebody using the traditional visualization software that the engineers use to try to seed streamlines. So there are limitations with the traditional visualization techniques and tools. For example, the engineers want to know where the reverse flow is. Where's the flow going backwards? And you cannot ask a very simple question like that with the standard tools, like show me the reverse flow, because the reverse flow is destructive. It takes away energy, takes momentum out of the stream. But with this system, it's very easy to say, show me the reverse flow, right? They can just pick the velocity, the y velocity, for example, and pick the negative values of the velocity, and that's the reverse flow. And then it gets rendered in all the other views. So this is the user interacting with the system. Right now they are setting different brushes up in the parallel coordinates view, and they're saying, show me the reverse flow. So here it is. It's easy to select the reverse flow here, and then streamlines are seated at all the positions, the corresponding positions of the reverse flow. And then we see, oh, there it is. That's where the flow goes backwards. Now, it doesn't always go backwards. It's hard to see, so that's why we've added some more visualization enhancements. So the seeds are here, the flow goes backwards, and it quickly turns around and goes downstream again, right? So there you can see it very clearly, right, with a distorted view of the geometry. So it goes backwards and then it goes back down. But to do that with the traditional software would be very difficult to find those positions where the flow goes backwards. And so the question is, can this design be altered in any way to minimize the reverse flow? Because the reverse flow takes away the momentum out of the marine turbine, the flow going through the marine turbine. So in this case, the user has selected the position of the blades. Those are the blades of the marine turbine. They're just depicted as discs. We won't go into the reason why they're depicted as discs in great detail, but that's what the engineers have decided. It shows the average position of the blade over time. And they average the position of the blade, and they average the fluid flow going through that, crossing that area over time. And it simplifies the calculation and makes it quicker, basically, rather than trying to do the individual blades. So that's an example of interaction with coordinated multiple views. You can also have a look at that on the DataVis YouTube channel. Any questions about that? Looks exciting, doesn't it? It's very applied. It's not so theoretical. It's like really trying to help with sustainable energy, for example. Okay, any questions about information visualization? So that's the end of the information visualization part of the module. Everybody excited about that? We could keep going. We could have a module just on information visualization. When I was a student, I always fell asleep in my lectures. I found that, like, in my first year I was awake. In my second year I was less awake. And then when I was a master's student, I fell asleep. Like the more I went along, the more I fell asleep in class. And at some point I thought, wow, I'm falling asleep in every single class. This is crazy. So I started to bring coffee to class. Does anybody else do that? I wouldn't do the energy drinks. That's not very healthy. Coffee is not quite as unhealthy as the energy drinks. Okay, good. So we're going to start the next part today on volume visualization, which is much different than information visualization. Much different. So we're not going to start with slides. We're going to start with a very cool video. One of my favorite videos of all time. This is a preview of what volume visualization can look like. This is what it can look like. Not all volume visualization looks like this, but this is one fun example. So volume visualization is no longer abstract data, but it's volumetric data. So it has X, Y, Z spatial components. And that's medical visualization is one of the compelling applications for volume visualization. Right? You've already encountered some forms of volume visualization if you visited the hospital. Right? X-rays are a kind of volume visualization, but they're not interactive, right? You just get one snapshot. This is an interactive volume visualization, but it's in a virtual reality setup. So this is actually like a virtual reality projection. That's a person, even though it's very hard to see that person. And that's a virtual clipboard. So it's a clipboard. But there are no actual buttons on there. The buttons are projected and rendered onto that virtual clipboard, so the user can interact with the visualization. So here you can see they have a stylus that they're using to interact with the clipboard, holding it in one hand, right? And then selecting different subsets of the volume. So there they've selected the skin, and now they've selected something, the hard tissue or the bones. They've increased the density of the selection. There they've moved it back to the skin again. They're sliding it. Now they're adjusting the transparency, right? So to make the surfaces transparent. And they're rotating the volume. Right, so they can adjust the transparency and then use this 3D interaction tool to select the object in 3D and rotate it around. It's pretty funky, isn't it? Like to have 3D selection. That's very unusual, at least in our day-to-day lives, that's very unusual. In virtual reality, it's not so unusual. So this is a different part of the data. That's the torso, right? And we can see different parts of the torso, like the ribs and the different, like lungs and respiratory system and kidneys, I believe, is one of the pieces. This is a clipping cube, so the user can reposition the clipping cube in different places. And then what's inside the clipping cube is more opaque than what comes outside the clipping cube, which is more transparent. Right, and this is the user selecting different parts or different objects inside the volume. So lungs, for example, or other kinds of soft tissue. So this is selecting the blue and the red and so on. Now at least you can see the person. So now we see kidneys. We can have kidneys be the focus of the visualization. And this is the user using the clipboard as a cutting plane operation. Right there, the kidneys. If you ever wondered what kidneys look like, a person's kidneys. Right, and then the user selecting that object again and rotating it, and then using the clipboard again to clip away the bone structure or make it more transparent. So this is a time-dependent volume visualization. Anybody recognize that? What that is?
Heart.
A heart, yeah. So it's a beating heart being rendered in real time, and this is the user interacting with that data, right? It's been scaled. It's not actual size, right? It's much bigger than actual size, and we can explore and analyze and manipulate the beating heart in different ways, render it from different angles, and select different features and so on in real time, 20 frames a second. Does that look interesting?
Yeah, is this being used nowadays in hospitals maybe?
That's a very good question. I actually am not 100% sure of the answer. I know that some of the developers that worked on this left the research world of research and went to work for actual medical organizations to commercialize it. But I don't know how far they got, like if it actually gets used in a commercial institution. I can tell you that there are some kinds of volume visualizations, interactive volume visualizations, used in medical practice. Some of them. Not this particular one, however, I would say. Like the virtual reality part is not. But some of the volume visualization is, yeah. Elsa?
Sorry, what's the reference for this article? Was it right to look at?
There's actually no reference to this. It's a video, and actually this is a unpublished video. But you'll find references to related material in the slides, in the slides that are being passed around.
That was VR, with the use of VR, so.
There are no references to the use of virtual reality in this module. Only volume visualization. So virtual reality could be a separate module. It's a separate field of research. This is showing the combination of volume visualization with medicine and virtual reality. So you'll find references to the volume visualization part and the medical visualization part in the lecture notes, but not virtual reality.
Is there a lot of research between volume visualization and visual reality?
There's a lot of research that combines virtual reality with visualization. Yeah. And in fact, we're in discussions with a company right now about combining these two things.
Thank you.
It's an exciting topic. I just show this video because I think it's so amazing. I love to watch this video. But this, I don't believe, is published in the public domain anywhere, not that I know of. I just happened to work at that company, this one, before I came here. So I got a copy of it. But that's a cool video. I would like a copy of that. Yeah, so you're a privileged group, a very special and privileged group. I remember the first time I saw that beating heart, and I I was blown away. Just thought that is so amazing. Amazing. Okay, so let's start looking at the slides. We won't cover the whole lecture right now. I can see that everybody's really excited to continue working on assignment 1. Yep. You don't say that over here. You have ants in your pants. You don't say that here, do you?
Yeah.
You do? Do you have ants in your pants to work on assignment 1? That's a slightly different here, because it wouldn't the literal translation would be ants in your trousers, but that doesn't sound. I guess it's more intense here, ants in your pants, but in the U.S. it would be ants in your trousers. I'll stop rambling. So we're talking now about volume visualization. Right, so we have 3-dimensional, 3D spatial dimensional data, but we're projecting it onto a 2-dimensional display. That actually should be an arrow pointing from left to right. Now, in some ways, volume visualization is all about this projection process. How do we take that 3D data and project it onto the 2D screen or the 2D display space? How does that work? That's the one-sentence summary of volume visualization. How do you project the 3D data onto the 2D display or the 2D projection space? And there are lots of different ways to do that. We're only going to talk about 2,000 ways to do that. No, we're only going to talk about a few different ways to do that, but there are lots of ways to do that. And how you project and what you project are inherently tied together. So you saw that there were different things being projected onto the 2D display in that video. Like sometimes the heart was being projected, sometimes the skin was projected, sometimes the bones, sometimes the kidneys, right? Sometimes it was being twisted around. So how does that projection work? There are different projection methods. Like one's called maximum intensity projection, one's slicing, one could be extracting surfaces, and also the topic called volume rendering. So volume data is 3 spatial dimensions, but it's all usually the same. For example, the density of the volume is one example, or the temperature or something like that. That means we're usually dealing with scalar data, right? And how do we see what's inside? That's the big question. And what we want to see depends strongly on what the user is interested in. So we want to be able to see the different things, and the user should be able to decide what information gets projected from the 3D to 2D. Where do we see this being used in medical applications, computer tomography, magnetic resonance imaging? You've heard of those machines before, right at the hospital. I think Swansea got its first MRI machine just a few years ago.
Really?
I think so. Yeah, exactly. It was just a few years ago. It's a big new MRI machine.
Oh, I knew it, maybe. Marston's had one for years, more than 5 years.
Are you sure?
Yeah, they also have a mobile one that goes to Marston for the excitation and to Singleton.
I remember reading about that in the newspaper, like the arrival of the first MRI machine in Swansea. Maybe I've lost track of time, exactly how many years ago, but it's been definitely since I've been working here at Swansea University. And I think there was some dispute about whether it should go to like Singleton Hospital or Morrison Hospital and so on.
They can do both.
Yeah, that would be the ideal solution. I actually remember one of the staff members here at Swansea University coming to give a lecture announcing the arrival of the MRI machine. So that was, you know, fun. And then he said like he was looking for volunteers for people to go and get scanned so they could use the data for research. So you can find 3D volume data in engineering, right? Material testing and control. You can find volume data in more fields of engineering like computational fluid dynamics and finite element methods. The finite element method, has anybody ever heard of that before? That was actually invented at Swansea University. So it's kind of quite famous. It's used all over the world now. So that's probably the most famous thing to come out of Swansea University in its history. I'm gonna guess. So the engineering college is very well known at Swansea University, and that's the reason. But they are desperate for data visualization because they're producing all this volume data, and they're desperate for data visualization. So the data is usually, not always, but oftentimes placed on Cartesian or regular grids. So that means dx is the space between data samples along the x-axis, dy is the space between data samples along the y-axis, and dz is the space between data samples along the z, or the depth, right? These are usually the same. Sometimes dz is greater, the space is greater along the z-axis, but usually it's resampled onto a uniform grid, right, to make it completely uniform in all three directions. And we are going to talk about that. Data can be arranged on cells or on voxels, so if the data is at the center of the cells, or the center of the cube, so to speak, it's called a cell, and if it's at the corners of the grid, then the units are called voxels. Has anybody ever heard that term before, a voxel? How did you hear that before?
Some paper. Computer graphics.
Nice. So Mark talks about it. Very nice. Do you remember what it is?
It's like a pixel.
A point in 3D space.
Exactly. A volume element, right? So a pixel, anybody remember what pixel stands for? I'm sure there's somebody in here that remembers pixel. You remembered voxel. Do you remember pixel? But where does the word come from? It's harder for you to answer that question. Picture element, right? That's where pixel comes from. So voxel is a volume element, right? And there are also unstructured grids, right, that are not so Cartesian and nicely laid out, right? They can be called curvilinear grids or unstructured grids. And the data is not conveniently placed on these cubes or based on cubes, but on tetrahedra or hexahedra. Does anybody know what a tetrahedra is? Anybody want to say what a tetrahedra is? It's here on the slide. It's a trick question. It's like a pyramid. Right? You can imagine a pyramid shape. Right? That's a fancy definition of tetrahedra. Okay, I think that was just a preview of the volume visualization that's to come. It's the next phase of the module. And we're going to talk about it in detail when I get back. Happy Thursday, everyone.